Hello everyone, I am Radha Kumari Pani, Assistant Professor at VIT. So last class we have already discussed about the entropy, how the entropy behaves like in a mixing of two elements in a systems at melting point or boiling point, how we can calculate the entropy, okay, and what is the residual entropy here, Kb, Ln, W, the formula here it is. Here your Boltzmann's constant and W is the number of configuration or arrangement, and W we can calculate by the formula that is permutation combination NCA. Okay, so in today's class we'll discuss about the stability of phases in single component system. Okay, first before going to what is phases, what is component, we have to know Gibbs phase rule. Okay, in Gibbs phase rule it is clear how you can calculate the number of component in a system or number of phases in a system. Let I am giving you small example. Let water systems. Okay, in water system H2O, it has three phases. One is solid, one is liquid. Generally, okay, we can say it is three phases: solid, liquid, and gaseous. So we can say the system, water system, contain three phases, and the number of component. Number of component means what? Component means independent variable. Okay, component means nothing else. It is the independent variable which can determine the phases. Okay, which is present in the phases. So only one component, that is H2O. Okay, so H2O system is a one component system or single component system. Like also we have binary system which has two component. Okay, in further classes we'll discuss about the binary component, what are the phases and how it is changes in applying the temperature and pressure graph. Okay, so now in a single component system, it is the temperature pressure graph. You can see how the system is changing. Okay, it is the temperature and by slowly increasing the pressure, three system it is given. Okay, one is gaseous, one is BCC structure, and another one is delta BCC, another one is BCC and HCP structure. How it behaves by constant temperature, if you are increasing the pressure slowly and slowly, how the system behaves. Okay, in a single component system. See, first it is the slope is in upwards, means by at a constant temperature, if you are increasing the pressure, the slope also increases. But at some time, the gaseous, by increasing the pressure, it will go to liquid phase. Okay, in the liquid phases, the slope you can see it is in horizontal line. Okay, the slope, it is nothing like upward direction, it will behave like a horizontal line. Liquid, because it is at constant temperature, if you are increasing the pressure, the gaseous will convert to liquid phases. Okay, which has lower volume. So it shows the stability of the phases. Okay, then in the second graph we can see the phases. Let it is FCC structure. FCC structure means the lattice point. The lattice point are in the corner, 8 corners. Okay, in the cubic like cube structure, it has 8 corners, lattice point, and each faces it has 6 faces. Each phases it has one face centered lattice point. Okay, it is FCC. In FCC structure, see, you have the cube like this. What happened in FCC structure means the lattice point are in 8 corners like this, and one centered face centered lattice point. Here front face, here let back face, here it is upward, here it is downward. 6 faces mean total lattice point 8 plus 6, 14 lattice point in FCC. Okay, so FCC how it is behaves by increasing the pressure at constant temperature. See, the slope is increases, then now in some pressure the slope will be behaves like in downward direction, this from this to this. Okay, because the phase field here it is closed packed structure shrink under high pressure. Okay, some system it will be expand under high pressure, so the slope goes in upward direction. But some phases, like some systems, it will be shrink under high pressure, so the slope will be upward to in downward direction. So now see, one is HCP structure. HCP means hexagonal close packing structure. Okay, this structure it will behave, the slope will be downward under the high pressure. This HCP structure it will be the slope will be in downward direction. Why? Because it is higher packing fraction. What is the packing fraction or packing fraction efficiency? In solid state, packing fraction means nothing but the volume occupied by the lattice point in a given system. Okay. In HCP structure, the packing fraction, it is high, like 74%, like something like this. In FCC or HCB, the packing fraction is more because the lattice point, the volume or the space occupied by the lattice point in FCC or HCB, it will be high. So the slope here, it will be in downward direction because the packing fraction, it is high. Now, the Gibbs free energy, that is the term, how the Gibbs free energy, it is most important to determine the stability of the phases. So now let's consider the isolated system. Isolated system means no heat is involved or no heat is equal to the surrounding. Okay, in isolated system, no heat transfer is going out. So every isolated system, it is tries to maximize its entropy for the stability. Okay, if the entropy is more, then the del G will be negative because the equation we know that del G is equal to del H minus T del S. More the entropy, more negative term, so more del G will be in negative side. So now instead of considering the isolated system, let's consider the open system where the heat is going to transfer to the surrounding and the heat also it is absorbed from the surrounding. So the transformation is possible when the del G will be in negative. Okay, the del G will be in negative. For the del G will be negative, the del S should be greater than 0 or the entropy should be in positive direction. So total entropy will consider the ds for the system and the ds for the surrounding, it will be greater than 0, means ds is positive. This is the condition for any system the transformation is possible or the reaction would be spontaneous. The condition should be ds in positive direction. So now in a reversible process, we know in a reversible process the entropy is 0. Okay, for the every reversible process the entropy will be 0. Reversible process means the system cannot, like it can transform back to its previous state, to its original state, or we can say to its initial state. But in irreversible system, the system cannot be transformed to the its initial state. For the irreversible system, the ds will be in positive direction. Okay, the ds will be in positive direction, or we can write ds will be greater than equal to 0 for the irreversible process. So now if ds is greater than 0, from the thermodynamic third law of equation we can write ds, the surrounding, it will be minus del q by dt. It is one of the equation of thermodynamic. We can calculate the entropy if you are knowing the temperature and you are knowing the change in heat. So now the equation we get ds is minus dq by t. Okay, so for the isobaric system, in the place of dq we can write dh. Okay, we know that from the thermodynamic first law of equation, dq is equal to dh minus, later we can write vdp. So at isobaric system means at constant pressure dp will be 0. So dq will be dh. So in the place of dq we can write dh. So now the equation will be ds will be greater than dh by t. So now dh minus t del s. If you are ds, you are taking ds to the right hand side, then the symbol will be changes. It will be less than equal to 0. So we know dh minus tds, it is nothing but it is dg. We have derived in the previous classes, that is dh is equal to dh minus tds. Now let considering the isobaric system, if you are considering the transformation at a particular change of temperature, okay, we are considering the system how it will behave at a changing temperature, we can write dh minus tds minus sdt. But at isotherm, at constant temperature dt will be 0. So now the equation will be dh minus TDS is less than 0 and dh minus TDS is nothing but that is dg. So now it is the new equation for any transformation is spontaneous or reversible. The condition should be del G will be less than equal to 0. Okay, in a reversible process such that any allotropic transformation like solid to liquid or liquid to solid, that will be possible if the free energy change or the del Z will be less than equal to 0. This is called the stability of any phases. Okay, the system should be in stable form, will be stable when it has minimum free energy. So now stability of the phases in single component system, we have here, let this graph. Okay. So now what is the we know the specific heat. Okay, specific heat, it is del H by T. From the previous slide we have derived the specific heat at constant pressure, it is dH by T. So now consider the two system. Let here this graph from we have let heat capacity from the liquid, it will be heat capacity for the liquid, it will be high, the heat capacity for the solid. Why? Because the liquid phases, okay, it will require more amount of heat to change the temperature by 1 degree. From that of solid state, liquid require more heat. So Cp for the liquid will be greater than that of Cp for the solid. So that the slope for the Cp for the liquid in higher form, C, then for the solid state. So now the free energy changes. Okay, the free energy changes for the liquid phases and for the solid phases, it will behave like this. The free energy changes for the liquid phases, it is in dotted form, you can see, and here the solids line, it will be free energy change for the solid state. At some temperature, it will meet, means at this temperature, GL is equal to GS, that is the temperature is known as melting point. Okay, at melting point, the free energy changes for the solid and the free energy changes for the liquid phases, it will be equal. So now it is enthalpy, like gives free energy, enthalpy, the slope of the enthalpy in upward direction, because at constant pressure, if you are increasing the temperature, the enthalpy will be increasing. So here the enthalpy for the liquid phases, it will be greater than that of enthalpy for the solid phases, and the difference between, it is the difference between, see, it is enthalpy for the liquid phases and it is the enthalpy for the solid phases. So the difference between the two phases is known as latent heat of fusion, or L. Okay, the symbol is L. The difference between the enthalpy of the two phases, that is the liquid phases and the solid phases, is known as latent heat of fusion, or we can say L. See, from this graph, let the graph between H, S and G and the temperature. Okay, if I are increasing temperature, how the enthalpy and the entropy and the Gibbs free energy, it is changing. So now it is the specific heat capacity at constant pressure, that is dH by dt, we know, and the previous equation, that is G is equal to H minus Ts. Okay, if you are increasing the like variation, differential of del G will be dH minus TdS minus HDT, and the H is equal to E plus PV, we know, H is equal to E plus PV. So dH we can write dE plus PdV plus VdP. Okay, this. In the place of dH, we can write dE plus PdP plus VdP. Now, this is the same, minus Ts minus SDT. Now, dE is equal to internal energy, that is dQ minus PdV. From the thermodynamic first law of equation, we know total heat, it is absorbed by the system. dE plus the work is done given by the system. PdV, it is the work done. Okay. So, in the place of dE, we can write dQ minus PdV. The minus PdV plus PdV cancel out. Now, also the entropy equation, dQ by T is equal to ds. So, in the place of dQ, we can write TdS. Now, the final equation we get TdS plus VdP minus TdS minus SDT. Okay. Here, plus TdS minus TdS cancel out. So, the final equation we get dZ is equal to VdP minus SDT. So at constant pressure, the slope of the free energy at constant pressure dp will be 0. So the equation we get dz is equal to minus s dt or del g by del t. At constant pressure, it will be minus s, that is the slope here. dg by dt, it will be minus s. So we can derive the equation also. From this equation, we can derive another equation, that is dh is equal to vdp minus sdt. At constant temperature, this term will be 0. So dg will be vdp. At constant temperature, dg by dp, at constant temperature, the term will be volume. Okay, from this equation, we can derive the two new equation at constant pressure and at constant temperature. And this differentiation between these two slope is known as Ts, because dg is equal to dh minus tds. So this is the enthalpy and this is the free energy term, and the difference between the two slope we get Ts. Now, see, let us consider the two different state. Let's state 1 and state 2. How we can say the system till going from the state 1 to state 2, it is stable if the free energy changes. Okay, the free energy changes, but the difference between G1 and G2 should be in negative, del G in negative direction, or it will be 0. Then we can state that the system is spontaneous and also it can transform the state 1 to state 2. Let's take example. State 1 is the metastable state, like the example like diamond or metallic glass we can take. And the state 2 we can say the most stable state. Why? Because G2 in the minimum form. Okay, here for the state 2, G2 is minimum from that of G1. So we can state most stable state. It is the most stable state, and here it is the metastable state. Okay, so the difference between the G1 and G2 we can take, this is del G transformation. It is in negative form because del G will be del G final minus del G initial. Okay, so we can say G2 minus G1. Okay, and G1 we can see G1 is greater than G2. So the G2 minus G1 will be negative. So that the system is spontaneous. We can transform from the state 1 to state 2 because the G2 minus G1 is negative. The difference between the gives free energy is negative. And this term, this is called the del G hump, or we can say that it is the activation energy. Okay, that is the activation barrier between the two states. So this is all about the gives free energy. Okay, how it will recommend the stability of any phases if the one condition del G is in negative form or ds will be in positive form. Okay, in the next classes we'll discuss about the Clausius-Clapeyron equation. Okay, this is the most important equation for stability of the phases. This is the in the form of pressure and temperature. In the next class we'll discuss about this and the application of this equation. Okay, so till then, take care, bye bye.